The point is locally, if I know roughly where I am, I can tell exactly where I am from this. So it almost doesn't work here, but it does work. And it'll always work. That's what implicit function theorem tells us. Always. So it'll always work if I have a holonomic constraint. I will always be able to do this at least locally if I have a holonomic constraint. That's not the case. It'll only not work when the constraint is not holonomic, when there are velocities in the constraint, and when the velocities can't be gotten rid of from the constraint. I'll show you an example in a minute, but first, one last example of a holonomic constraint. X equals r theta is holonomic, right? X and theta are related there in a way which doesn't include x dot or theta dot. However, here, when I started proving it, I had something with x dots and theta dots in it, but I could integrate them out, and when I integrated them out, I got something holonomic. If those dots had not been integrable, if I couldn't get rid of them, it would not be holonomic. And a nice intuitive way of finding out that it's not holonomic is checking. Can I really reduce the number of parameters required to parameterize the system? And if I can, it's holonomic. And if I can't, it's not. And here's an example of something that isn't holonomic. Same system, ball rolling around without slipping in a two-dimensional plane. I'm not going to pick up that dustbin again. But if I did, and I rolled it around in a circle, that's an example of something that is non-holonomic. Why? Well, there are a lot of ways to prove it. I can prove it basically the same way as I proved this. I start with velocity constraints, but then I can show that they're impossible to integrate out. It's impossible to change the v equals naught thing into something that only includes the positions and the velocities. But another, much simpler argument just says, I cannot reduce the number of parameters required to specify that circle rotating in space for the following reason. And I'll draw a picture here. An example of a non-holonomic constraint. I've got a plane, right? Here's my plane. And I'm rotating a disk around on the board. Does anybody have something circular that I can rotate that is not disgusting? Circular objects. Bottle cap. Right. So this guy is going to rotate around on the board, right? He's not super small. Ah, there's something. Right. So let's look at this circular object. It's rolling without slipping on the board. Here it goes, right? So it's rolling along without slipping, and it can change its parameterization in x and y as it goes. Right. Now, what are the parameters needed to describe the orientation of this thing? Well, I need to know where it is. X, y, its rotation this way, and its rotation that way. Does that make sense to everybody?
No.
X, y. So to completely specify where it is, I'm very chalk. Does someone want to hold this thing? Because I don't want to mess it up. Okay, that's a chalky hand. Okay, right, so it can rotate x, it can move to y, right? Once it's at some position on the board, it can also rotate this way. See? And it can also, of course, rotate this way. So to completely determine where it is, I need to give its x location, its y location, this rotation, and this rotation. Correct? Good. So you mean like flipping out the place? So okay, so let's assume that it's stuck to the place. So let's assume that I'm not lifting it off the floor, and let's assume that I'm not rotating it so that it falls over. So I'm assuming that it's always maintaining a contact like this. So how many parameters is that? 4. What I say is, the number of degrees of freedom of the system of this bangle moving along the board is 4. It's a 4-dimensional configuration space, 4 degrees of freedom, 4 generalized coordinates, all means the same thing. We'll cover, of course, in some detail now. If the rolling without slipping constraint was polynomial, then by the implicit function theorem, I can write one of those constraints in terms of all the others. In other words, I could essentially eliminate it. And I could reduce the number of things I needed to 3. Does that follow with all of you? Yes. So, can I? Here's the question, right? When it was rolling along in a straight line, I could. All I needed to know was how far it had traveled along the line, and by the fact that it had to roll all the way there, I could determine its angle. Does that follow? But now it's rotating in a plane. And I'm going to show that I can rotate this thing around in a circle, bring it back to exactly where it was before, except slightly rotate it this way. In other words, all the other parameters are constant, but one of them has changed. And if that's true, that parameter can never be expressed in terms of the others. Because while keeping the others constant, I've changed it. So let's do that. I'm going to start at a location. Now, imagine, okay, I'm going to keep my fingers fixed on one point on this thing. Imagine my fingers like a marker. Fixed at one point. When I begin my motion, my fingers are vertically outwards from the screen. And I begin my motion at the X. Now I'm going to roll around without slipping in a circle. Boom, bump. I have to spaz around here. It's actually quite difficult. You know what? I'll mark the point like this. That'll make it easier. Then I won't have to spaz around. So, marking a point, I'm rotating it without slipping. Actually, I need a helper. Level. I'm going to keep marking out a point on the X as he rotates it. So I'm marking out a point, he's rotating it around without slipping in a circle. There it goes. Moving around. And coming back around. Oh yeah, this is a race to do in a minute. Right, so my finger is over here now, which is in a different place to where it was when we started. What does this mean? It means that even though I rotated it around, and when it ended up, in that same rotation as it was when it started, it's still pointing vertically, it's still at this point in the XY plane, so it's still rotated this way in the same orientation, but what's different is the way it's rotated this way. So, I've executed a motion of the system, obeying the constraint, from one place to another, and changing only the value of one coordinate. In other words, no coordinate can be written as a function of all the others, because I've kept all the others constant, and one has changed. So, the constraint of rolling without slipping in 2 dimensions is not not used.
For 2D objects shown like that, we have to validate the
Okay, it's very hard for me to demonstrate on the board, but get hold of a wheel and do it yourself. You'll find out. Like not that wheel, but like a, you know, if you have some circular object at some point in the spare time, you know, turn it around the circle, check it out, observe, mark a point on it, see what happens. You'll notice that you can execute a motion without violating constraints that actually does bring it into a different configuration. Now, there is a formal proof of this mathematically. It involves the non-integrability of the constraints when I write this thing. I'm not going to show it to you now. It's just going to distract you on purpose. But it will be in the notes. So you will, those of you who are a bit skeptical and are like, yeah, he's rotating bang off. those of you can go and check out the notes, and there will be a mathematical derivation when those notes are uploaded. I'm going to move on quite a little bit now, because I want to leave you guys with a good understanding of generalized coordinates. And then we'll have the touch. And of course you'll have a small break before the touch, because I know how important breaks are. So I'm really going to do this. So what we've seen is constraints, forces of constraints, equation of constraints, holonomic versus non-holonomic, and we now have an inkling as to a holonomic constraint reducing the number of parameters that I need to describe the system because of this implicit function theorem. It allows me to use less and less parameters, fewer and fewer parameters to describe the same system, provided that I know what the constraints are. Now I haven't talked about physics yet, I've just talked about locating objects. We're not going to talk about physics for a while because physics involves the equations of motion, the Lagrange's equation of motion. We first have to talk about something called generalized coordinates and the configuration space of a system. Now given some system, we've already talked about this one, there are a certain number of parameters we need to describe its configuration, where it sits. Those parameters are called generalized coordinates. We can choose all manner of different parameters. For instance, for the block on the slope, we could have chosen just x along the bottom there, or we could have chosen just x along the slope. Both of those would completely determine the motion of the system. For the pendulum, we could have chosen my x position and then worked out the y in terms of x, or the angle, theta. Those are both perfectly good generalized coordinates. The important thing is, generalized coordinates are the smallest number of parameters we need to parameterize the system, and we choose any parameters that work. By parameterize, what do I mean? It should be able to fully describe any configuration that the system can get into, right? And it should do so uniquely. And it should do so in such a way that there are no constraints, no holonomic constraints between the coordinates that I've chosen. So, for the block on the slope, y and x, are these generalized coordinates? The answer is no. The reason is because there are two of them, and because there exists a holonomic constraint between them that we've written down up there. So they are constrained in some way. Generalized coordinates never are. They're always free to move however we like. So let's remove one of them and just keep y. Is that a generalized coordinate? The answer is yes. When I know the height of the block, I know exactly where it is, because I can work out x in terms of y. Right. If I just kept x, is that a generalized coordinate? The answer is yes. When I know how far the block is along, then I can determine how high it is. If I had just chosen this, the distance traveled down the slope, let's call it q. Is that a generalized coordinate? Yes. When I know how far I've gone from the top of the slope, I can work out both the height and the distance from that, because I know the angle of the slope. Right, so there are many different coordinates one might choose to parameterize the system, and they will be called generalized coordinates if they fully describe all the possible motions of the system, and there are no holonomic constraints between them. Because of the implicit function theorem, and because of some deep results in manifold theory, in fact, no matter what generalized coordinates you choose for a system, there will always be the same number of them. Over here, there was always one. Whether it was this one, or that one, it was always one. For a pendulum, it's also always one. I can choose the angle it swings at, the x displacement of it, the y displacement of it. Always one parameter. For a particle moving in the plane, it's always two. Whether I choose Cartesian coordinates, polar coordinates, or elliptic coordinates, I have two coordinates. The number of coordinates needed to specify a particle is called the dimension of its configuration space, or the degrees of freedom. And it is the number of generalized coordinates needed, no matter which ones I choose, to fully specify the position and configuration of a particle. I'll consider a few examples. A double pendulum is a pendulum attached to a pendulum. When I swing the top here, the first rod swings around and the second rod swings underneath it. How many degrees of freedom? 2. Right? I need 2 coordinates to fully specify the configuration of that system. I can give them, for instance, as these 2 angles, but I could give them as a lot of different things, right? So it's 2. 2 degrees of freedom. If, however, and this is an important one, if I now, instead of letting this thing wiggle around on its own, specify some path for the first one, right? So I give the first one to you. I force it to do this. I don't think so. I force it to do this. And then I let the second one vary however I like. Then I know without any coordinates, without any free parameters, exactly where the first one is going to be as a function of time. It's not free to move. I'm moving it. Right? So then this is no longer a coordinate. It's merely a parameter. And the only coordinate left will be this one. So if I specify theta 1 as a function of time, then it becomes a parameter. How many coordinates, how many degrees of freedom are there in the system then? 1. Only theta 2 remain. Other examples that I might think of. How many degrees of freedom are there? Inside it. When I take this labello and I throw it into the air, let's assume that it's not allowed to do that. I throw it into the air. Well, let me take a larger object, any rigid object. And I throw it into the air. How many degrees of freedom are there when I throw the chair around?
Can you please explain that line again?
Okay, so how many different ways?
Not that. When you specify theta 1, then
if I specify theta 1 as a function of t, let's say for instance, I start at the origin and I slowly move it outwards. And I'm completely controlling its motion. It's no longer a degree of freedom. It's no longer a coordinate. It's a parameter. The only thing that's allowed to change now is the other part of the pendulum, which swings freely. There's only one coordinate describing the motion. Now, if I took a chair and I moved it around, what can I do? I can change its x location, its y location, its z location. I can rotate it around like this. I can tilt it, right? And I can rotate it around on its own axis. So let's just look at those motions again. I call this x, x, y, z, right? And then there are a couple of others. Along the axis of the chair, let's assume the chair is pointing upwards. Looks like it's pointing upwards. Along the axis of the chair, I can rotate it. I call this rolling along its own axis. It can roll along its own axis. It can pitch up or down. And once it's pitched and rolled to a specific orientation, I can still move it around like this, which I call yaw. Yaw. These are called Euler angles, right? And they specify the orientation of a rigid body. So I go x, y, z, pitch, roll, yaw. So any rigid body has x, y, z, pitch, roll, yaw. If the rigid body is lying on the ground and I'm rolling it, you can see why the roll angle is called roll. And if it's lying on the ground, and I pitch it upwards, you can see what a pitch angle is called pitch. And I don't know why the Euro angle is called Euro. Right. So there are 6 degrees of freedom for a general rigid body moving around without the ability to move in space. If I consider the zero, it's a rigid body with a difference. What's the difference? This part can move out of it. Let's say that the lid can't come completely off. Let's say it's constrained to remain on. So it can't fly off and become 2 rigid bodies. Then I've got X, Y, Z, pitch, roll, yaw, and angle of extension, distance of extension of the joint. So that's how many degrees of freedom? 7. Something that is rolling on a line without slipping. And how many degrees of freedom? What? A ball rolling on a line without slipping. This guy that's rolling around, no slipping, how many degrees of freedom? Initially you need 2, right? You need to specify X directed X position and an angle theta. But when I specify that it's not slipping, and because it's doing so along a line, and because when I specify the constraint along a line it was holonomic, I can reduce from 2 to 1. There's only 1 degree of freedom. I've now given you the answer to about 8 or 9 of the questions in your quiz. Right, so we'll stop there for the day. We understand roughly what generalized coordinates are, what degrees of freedom are, constraints, quiz available, test and use my tips. And something available in an hour's time. Taking a break. When we meet again, we'll be in the cut venue where you guys, I don't actually know, maybe we should meet again here.
Yeah, it's better here.